Okay, everybody, we're going to go on to sort of the next major operation in calculus called the derivative. So the idea is this. In previous sections, we dealt with average rate of change. So if you remember, that was just the slope formula from algebra. You had the slope is the change in the y's over the change in the x's. Okay, so to do average rate of change, you basically had to have 2 points on the graph. You had to have an x sub 1 comma y sub 1 point, and then you had to have another point, x sub 2 comma y sub 2. And you applied that formula and got the slope between the lines, or in other words, the average rate of change between those 2 points on the graph. What we want to do with a derivative is we only want to use 1 point. Okay, so think of it like this. I want both x sub 1 and x sub 2 to be the same. Okay, so they're both 5, for instance. So you'd have 5 minus 5 on the bottom. That would give you division by 0, which is a problem. But remember, when we did limits, we dealt with certain cases where we could actually get an approximate y value, or slope value, I guess I should say, in this case, for things that are divided by 0. More specifically, if you got 0 over 0, you were able to factor and cancel. So the reason we did limits was so that we could figure out how to do a derivative here. All right, so look over here in the gray box. This is just out of the textbook, the limit definition of a derivative. So for any given function y equal f of x, find the derivative of f at x is defined to be f prime of x equal the limit is h approaches 0 for f of x plus h minus f of x all over h. Okay, so first thing, what they're doing here when they say h is the distance between the two x values. Okay, so just like I said over here, I want x sub 1, x sub 2 to be the same. If they're the same, there is no distance between them. So literally what they're saying is they want h equal x sub 2 minus x sub 1 to be 0. Okay, so h represents 0 here. Up on the top, instead of y sub 2 and y sub 1, they're using f of x plus h and then f of x. These are just a different way to denote y values. F of x in algebra was the same thing as y. F of x plus h is literally, instead of just taking some value x and plugging it into the function to get a y value, you take an x plus h, but remember we want h to be 0 basically. Plugging it into the function and getting a y value there. So this is also a y value. So in essence, on top you've got y sub 2 minus y sub 1. And then on bottom, again, remember we said h is the same thing as x sub 2 minus x sub 1. So it's just a rewritten way to write slope formula, specifically for when the distance between the x values is 0. So h is going to be 0 here. All right, so what we want to do is look at an example using this limit definition of a derivative to approximate a derivative. So let's go down here to this example. Using the definition of the derivative, find the derivative for f of x equal x squared. So in other words, I want to know what the derivative of x squared is. Okay, so the way the book does it, they break it into 3 steps, I believe. I believe they call it the 3-step process in our book. So form the difference quotient, delta y over delta x. in essence, that's the slope formula. Delta y is the change in the y's. Delta x is the change in the x's. So in step 1 here, we're just talking about slope formula. We're not talking about limits or anything yet. Okay, so delta y over delta x is just the change in the y's over the changes in the x's. Now, again, they're not going to use the terminology y sub 2 and y sub 1. Okay. So here we begin with 2 points, x comma f of x. Let's imagine a graph here. Okay, so say right here you have x comma f of x comma y, if you will. And then another point, x plus h comma f of x plus h. So let's say it's up here. X plus h comma f of x plus h. Okay, so the distance between these 2 points is literally h. Okay, by substitution, again, that gives you that formula, f of x plus h minus f of x all over h, where h again is just that distance between the x values. All right, now where do they get this stuff? Here, right here. Okay, they literally figure out what f of x and f of x plus h is. Okay, so how are we going to do that? Well, if you look at the question, f of x is x squared. So that's where they're getting the x squared right there. All right, now where is this x plus h squared coming from? So think about it this way. If f of x is x squared, and I want to plug in place of x plus h, I'd have x plus h squared. Okay, so that is going to go in for f of x plus h. Okay, so that's where they're getting the numerator there. They get x plus h squared minus x squared all over h. Okay, step 2, they're going to simplify this. Okay, so they go from x plus h squared to x squared plus 2xh plus h squared. So how are they doing that? Well, think about what it means in arithmetic. X plus h squared literally means x plus h times x plus h. So you're going to multiply that out, or you might have called it FOIL it out in grade school. I don't know why they use that terminology, it just means multiply it out. Okay, so you'd have x times x is x squared. You'd have x times h is xh. Okay, then you'd have to go and take h times x, which is another xh. And then lastly, you'd have to take h times h, which is h squared. So you've got 2 like terms in the middle there. So you get x squared plus 2 xh's plus h squared. Okay, and that's what they're getting right here. X squared plus 2xh plus h squared. Okay, and don't forget you still have the minus x squared that you had previously up here. Okay. All right, if you look at this, let me get rid of some of these lines and things to make it a little clearer to look at. If you look at this, you've got an x squared here minus this x squared, so those subtract away. So it leaves you 2xh plus h squared over h. Okay, can you simplify this? In other words, think about what we're going to be doing in a minute. We'd want to be doing the limit as h goes to 0, because that's what we had up here for the definition, right here. In other words, you wanted that denominator to be 0. You wanted no distance between the x values. So if I wanted to do a limit as h approached 0 here, think about what would happen if you plugged in 0 for h. You'd get 2x times 0 plus 0 squared all over 0. That ends up being 0 over 0. So that tells us factor and cancel. So in the next step, they've done that. They've pulled an h out on top. It's going to cancel out with the h on bottom, so all that's left is just the 2x plus h. So this is simplified right here. Okay, after they've simplified the difference quotient, step 3 is going to be to actually do the limit. Okay, so right here, the limit as h approaches 0 for 2x plus h. If you plug in 0 in for h, you get 2x plus 0. No need to say plus 0 on anything, so we get 2x. So this is called the derivative. Okay. So the derivative of x squared is 2x. Now, what a derivative is supposed to represent is instantaneous rate of change. If you look in the book for the formula for instantaneous rate of change, what they're going to give you is this same definition. They're going to give you the definition of the derivative. The idea is this. The derivative is a function. So you still got x in it, if you will. Okay. If I wanted to, say, find the instantaneous rate of change when x equal, let's say 5, okay, then all we'd have to do is plug in 5 for x in that derivative, and we'd get 10. 2 times 5 is 10. Okay, so the difference between derivatives and actual instantaneous rate of change is this: the derivative is still a function. Instantaneous rate of change is going to be an actual numeric value. So they'll supply you some x value, whatever x value they ask about, and you basically plug it into the derivative to get the instantaneous rate of change. Okay, let's look over here at the next screen. The way we did derivatives in that first example, by the limit definition, it works, but it can be complicated. The more complicated your function is, the more complicated it's going to be to simplify that difference quotient. So they're shortcuts, and they're used so often they're just the way to do it. So the first major shortcut you'll see is the power rule. For the function x raised to r, where r is any real number, so basically x raised to any exponent, then the derivative is r times x to the r minus 1. Okay, so just to redo that example from the previous screen, we just did this function a minute ago. We got the derivative with the limit definition, x squared. If we do it with the power rule, I'm going to show you it's the same thing. Okay, so if r is the exponent, we moved r out front, so 2 went out front. Then we rewrote x, and then we subtracted 1 from the exponent, so we have 2 minus 1 there. Well, 2 minus 1 is 1. We normally don't write exponents of 1. So we're basically able to immediately go to the derivative, 2x. So this is a lot quicker than using that limit definition. So I wanted to show you that limit definition because it actually shows you what a derivative means. A derivative really is a certain type of limit. But we're going to use these shortcuts to actually work derivatives. So power rule is the most common one. Okay, so let's work some problems. Okay. Number 1, find the derivative for the following function. So I've got y equal negative 3x squared. Okay, so one thing that's a little different here is instead of saying f of x equal negative 3x squared, they actually said y equal. So typically what you're going to see is if they give you a function f of x, derivative is generally going to be written as f prime of x. If they give you y equal, instead of f of x equal, you're generally going to see that as dy over dx. This is called Leibniz notation. It's just named after the guy that came up with it. Dy over dx means exactly the same thing that f prime of x means. It means the derivative of the function. You may also see sometimes where they write y prime. Okay, I don't like the notation y prime because it's too easy to confuse that as y to the first. In later stuff in chapter 3, you'd see what I'm talking about, but typically I'm going to just use either function notation f prime of x or Leibniz notation dy over dx. Okay, so either one of those things that you see me write is going to indicate derivative. Okay, so I want the derivative here. Alright, now we already did the derivative of x squared. The difference here is you've got a coefficient -3 sitting in front of the x. The way derivatives work, you can always just bring down the coefficient. So I'm going to bring -3 down, and then I'm going to do the derivative of x squared. Derivative of x squared is 2x. So in other words, I've got -6x. There's my solution. Now I wanted to write this out one time where I'm showing you that I'm literally just bringing that coefficient down, that -3 in this case. You're going to get to the point when you do these enough that you're just going to go ahead up front and say -3 times 2 is the -6. Okay, so I mean that works too. I'm just trying to express here that the coefficient's actually just brought down and you're just doing the derivative of the x part. Derivative of x squared is 2x. Okay, number 2, same thing. We've got a decimal exponent, but that doesn't matter. It doesn't change the rule. So -4 could actually come down, and then the derivative of x to the 3.2 would be move the exponent out front, rewrite x, subtract 1 from the exponent. 3.2 minus 1 is 2.2. Okay, so we can go ahead and say -4 times 3.2 here is -12.8. X to the 2.2. Okay. And so it doesn't matter if you got a whole number exponent like in question 1 or a decimal exponent like in question 2. It's still the same exact rule. Number 3, they're doing a fractional exponent, 7/8, instead of a decimal or a whole number. But again, the rule doesn't change. Okay, so they're using g of x for the function here, so I'm going to say g prime of x to indicate derivative. Okay, 5 can come down. It's a coefficient. Do the derivative of x to the 7/8. So 7/8 can go out front. Rewrite x. And then we need to subtract 1 from the exponent. So go to the side here. 7/8 minus 1. If I want to add or subtract fractions, I'd have to have a common denominator. So let's think of 7/8 as 7/8, and let's think of 1 as 8/8. 8 over 8 is 1, right? So 7/8 minus 8/8 is -1/8. And so that's going to be my new exponent. And then let's go down here. Let's go ahead and multiply out. 5 times 7 is 35. So 35/8 x to the -1/8. Okay. All right. So same rule. It's just you need to remember how to add and subtract fractions. Okay. You have to have a common denominator. So 7/8 minus 1 is the same as 7/8 minus 8/8, which is -1/8. I'll give you a quicker way to do that with exponents. Think of it this way. If I've got 7/8, take the top minus the bottom. 7 minus 8 is -1. That's going to be your new numerator. The denominator always stays the same as it was. Okay? That'll always work if you want to do it a quicker way. Okay, here in number 4, y equals 4x to the negative 3. So let's go ahead and instead of writing the coefficient down and then doing the derivative, let's go ahead and think about doing the whole thing at once now. In essence, you'll have 4 times negative 3, which is negative 12. X to the negative 3 minus 1 would be negative 4. Make sure you're going the correct direction there. Negative 3 minus 1 is negative 4. Okay. All right, here's some more. Find the derivative for the following function, y equals negative 7x. All right, think about this for a second. X here, there's no exponent written on it. There's no exponent written on it. It's understood to be x to the first. Okay. So negative 7x is the same as saying negative 7x to the first. So if I want to do my derivative, negative 7 times 1 is negative 7. X to the 1 minus 1 is going to be 0, right? So the question is, what's x to the 0? Well, what's anything raised to 0? Anything other than 0 raised to 0 is 1. Plug it in a calculator. Type 5 to the 0 in a calculator, you'll get 1. Type 8 to the 0 in a calculator, you'll get 1, etc. Any number raised to 0 is always going to be 1, except for 0 itself. 0 raised to 0 is undefined. If you try to type 0 raised to 0 in a calculator, you'll get an error message. Okay, so my point here is this is really the same as saying negative 7 times 1, which is just negative 7. All right, and number 6, we just have a number there. Y equals negative 32. The book shows this as a separate rule. I'm going to show you that it's actually just the power rule again. So just like we said right here, x to the 0 is 1. I could rewrite this as negative 32 x to the 0, okay, and then try to take the derivative. Negative 32 times 0 is 0. X to the 0 minus 1 is negative 1. Doesn't matter. What's 0 times anything? 0 times anything is 0. So they call this a separate rule in the book, and they call it the derivative of a constant. Basically, the idea is the derivative of any number is always 0. Okay, so the derivative of negative 32 is 0. Number 7, same thing. We got 51 there. It's just a number. There's no x's in there. Okay, so the derivative is going to be 0. All right, number 8. We're getting into some stuff that's a little bit different now. We have 6 over x to the 5th. All right, what I want you to realize with this is, where's x at? It's in the denominator. It's on the bottom. If you look at the power rule, let me go back over here to it. Okay, when I gave you the power rule here, x right there was in the numerator. If you want to think about this as x to the r divided by 1, you might could visualize it better. X is on top. It's in the numerator. To apply the power rule, x has to be on top. Okay? It can't be in the denominator like we have here in number 8. So what we've got to do is rewrite this function where x is on top. Okay, and it's easy enough to do. We can move x up or down as long as we change the sign on the exponent. So 6 over x to the 5th is the same thing as saying 6x to the negative 5. Okay, and now x is written on top. So now that it's written on top, we can work it like we've done the previous questions. Okay. So 6 times negative 5 is going to be negative 30. X to the negative 5 minus 1 is going to be negative 6. Perfectly fine to leave your answer like that. Some calculus books out there always say, write your answers with positive exponents. Okay, so they'd want you to write it like this. That's all good and well. This is the same thing. But we don't have any issue with you leaving things in terms of negative exponents. So the way I have it circled right there, that's how I would answer it. Hawks accepts it that way. It's no problem to have a negative exponent. There's really nothing wrong with that. If you did choose to write it as negative 30 over x to the 6, it will accept that also. So you can write it either way, but you're just going to see me in these videos leave things in terms of negative exponents like I have circled. Okay. Alright, getting a little bit uglier. F of x equal negative 2 over the square root of x. Okay, so square root of x is the same as saying x to the 1/2. Okay. So I got rid of my radical sign. The power rule is written in terms of exponents. So you want to work your problems in terms of exponents, not in terms of radical signs. Basically, anywhere in calculus, BCal 1 or BCal 2, if you're given a problem with a radical sign in it, go ahead and change it over to exponents. Should be your first step for anything in BCal 1 or BCal 2. Now we still have an issue here. X is still on bottom, kind of like we had in number 8. So we're going to have to shove that up to the top. And it'll become negative 2x to the negative 1/2. And now we have the form we need. Okay, so now let's take the derivative. Okay, so negative 2 times negative 1/2, the negative signs would cancel. 2 times 1/2 is 1. X to the negative 1/2 minus 1. What's negative 1/2 minus 1? Well, that's going to be negative 3/2. Alright, now in math, we typically don't write coefficients of 1. So we actually don't want to type that in. We want to just type it in as x to the negative 3/2. There's no need to write a coefficient of 1. It's just not necessary. So there we go. That's what we want. Alright, down here in number 10, this is the first problem you see where you've got multiple terms. And this is kind of a segue into the next video. It deals a lot more with multiple terms than this section does. Most everything in this section is a single term, but you've got two terms here. You've got 8x as a term, you've got minus 7 as a term. In derivatives, there's a rule that says this. If I've got y equal something plus or minus something else, okay, that's two separate terms. Whether we're adding or subtracting them doesn't matter here. If I want to get the derivative, I do the derivative of the first term plus or minus the derivative of the second term. This is called the sum or difference rule. I'm never going to ask you to repeat the name of that rule to me. I'm just writing it down here for reference. But all it's saying is if I have multiple terms, I can just do the derivative of each term. Okay, so let's do that. So if I have 8x, the derivative of 8x is going to be 8. And if I have negative 7 is just a number. The derivative of that is 0. Well, we don't write plus 0, right? So our solution is just going to be 8. Just do the derivative of each term is all we're saying there. Alright, in the next video, we're going to continue on with similar problems to this. Most of them will be multiple terms like we have here at number 10 though.